Jupiter is not just another planet. It is a colossal engine of storms, radiation, and gravity, so massive that its pull makes the sun itself wobble in space. Understanding Jupiter means understanding why our entire solar system looks the way it does. Astronomers sometimes call Jupiter a failed star because its composition resembles the sun. Yet this so-called failure is a guardian, reshaping orbits, capturing debris, and quietly rewriting the history of everything smaller that circles our star every single day in space. The same gravity holding your body to Earth also choreographs Jupiter's motion around the sun. When Jupiter shifts slightly, the entire solar system responds, including the long-term stability of the worlds where chemistry became biology and eventually became us all. Now let's place Jupiter in space. It is the fifth planet from the Sun, circling at an average distance of 778 million kilometers, about 5.2 astronomical units, completing a single orbit every 1186 Earth years around our central star once. The planet's axial tilt is only about 3 degrees, so Jupiter barely experiences seasons. Its rapid rotation fattens the equator, giving Jupiter a noticeably larger radius at the equator than at the slightly flattened poles of this giant world today. Jupiter's size is impressive, but its mass is even more striking. It holds about 1,000th of the Sun's mass. Yet because the Sun dominates 99.86% of everything, Jupiter contains almost all the remaining planetary material in orbit today. Jupiter alone is 2.5 times more massive than every other planet combined. Because of that, the center of mass, the barycenter of the Sun-Jupiter system, actually lies slightly above the Sun's visible surface in space outside it. A barycenter is simply the shared center of mass. Both bodies orbit that point together. Imagine a long rod with a heavy weight on one side, lighter weight on the other. The balancing point always sits closer to the heavier end. While Jupiter has the greatest planetary mass, it is not the densest world. If Neptune were puffed up to Jupiter's size, Neptune would outweigh it. If Jupiter shrank to Earth's radius, Earth would be more than 4 times denser inside. As it is, Jupiter's diameter is about 11 times that of Earth, yet it packs in 318 Earth masses. At the visible cloud tops, gravity is around 2.5 times Earth's surface gravity, enough to profoundly compress its interior layers tightly. This immense gravity does not stop at its clouds. It reaches across the solar system, tugging on every planet's orbit to some degree, subtly modulating their paths and long-term stability over hundreds of millions of years of evolution there. Jupiter's gravity is strong enough to tear apart fragile asteroids that pass too close, and powerful enough to capture dozens of objects as moons. At least 67 natural satellites are confirmed, many likely fragments from these disrupted visitors today already. In the early solar system, that influence was even more dramatic. Many models suggest Jupiter's gravity disturbed forming planetesimals, breaking some apart, ejecting others, and preventing additional planets from coalescing. The battered protoplanet Vesta is a classic surviving example of that sculpting. Even today, Jupiter's distant pull slightly modifies Mercury's already eccentric orbit. Over billions of years, simulations suggest that this quiet tug could one day nudge Mercury into either plunging toward the Sun or being flung outward altogether in space somewhere. At the same time, Jupiter may be a quiet guardian of the inner planets. Its mass deflects or absorbs many icy visitors that might otherwise sweep through Earth's orbit, helping preserve the long, stable intervals that complex life appears to need. This is why Jupiter is often described as a cosmic vacuum cleaner. Long-period comets falling inward from the Oort cloud can have their orbits bent, sometimes captured, sometimes redirected outward before they ever reach the inner solar system regions. But Jupiter is not a perfect shield. Its gravity can also redirect some objects onto new paths that cross the inner planets. The statistics still favor protection, yet the interaction is a complex gravitational dance rather than a simple one-way barrier. Despite sitting more than 5 times farther from the Sun than Earth, Jupiter outshines every star in the night sky. At maximum, it reaches magnitude -2.94, bright enough that it can project faint visible shadows on dark nights outside. So even a simple handheld camera or small backyard telescope can reveal Jupiter. Through consumer instruments, bands of cloud become clearly visible, and the 4 largest moons appear as bright points, sliding back and forth in a miniature solar system every night. Light leaving those clouds on Jupiter travels nearly 3/4 of an hour before reaching Earth. That same stream of photons can strike the sensor of a camera or the retina in your eye tonight, connecting you directly to that distant world. But what are those colorful patterns we see? Jupiter's visible cloud deck is only about 50 kilometers thick, composed mainly of ammonia crystals. Rising gases from deeper layers deliver chemicals that stain this thin blanket into alternating bright zones and dark belts. These compounds, called chromophores, likely include complex sulfur and phosphorus-bearing molecules. Heated far below, they rise, then sunlight's ultraviolet photons break and rearrange them, generating the ochres, whites, and browns that stripe Jupiter's face in parallel bands around the planet. The latitudes of these bands remain remarkably stable over time, so observers assign them standard names. But their widths and colors can change dramatically, as powerful winds and vertical flows churn the boundaries, spawning turbulence where lighter rising gas meets darker sinking currents. Out of that turbulent interaction rises Jupiter's most famous feature, the Great Red Spot. This gigantic anticyclonic storm has raged for at least 3.5 centuries, wide enough to easily swallow the entire diameter of Earth within it. The Great Red Spot towers higher than surrounding clouds, giving it more direct sunlight. That height, combined with unusual chemistry, may explain its stronger color. Modern measurements show the storm is shrinking, yet it still spans more than one Earth's width today. The exact cause of the Great Red Spot's hue is still debated. One leading idea suggests that solar ultraviolet light alters ammonia and other trace chemicals, producing reddish compounds concentrated at the storm's top, where they endure more intense illumination than neighboring clouds. And Jupiter does not have just one long-lived storm. Between 1998 and 2000, 3 smaller white ovals merged to form a new vortex observers nicknamed Red Spot Jr., which later reddened and now orbits nearby, enduring alongside its older, larger neighbor. These gigantic vortices are natural laboratories for fluid dynamics. Winds exceed hundreds of kilometers per hour, rotating for decades without decaying. Studying them helps scientists understand not only Jupiter's atmosphere, but also weather on brown dwarfs and gas giant exoplanets orbiting other stars. Beneath all this weather, Jupiter transitions through exotic forms of hydrogen. Starting as molecular gas at the top, hydrogen becomes densely compressed liquid deeper down, then under crushing pressures transforms into metallic hydrogen that can conduct electricity like a metal within the planet's interior. At Jupiter's center likely sits an ice-rich or rocky core tens of Earth masses across, though its exact size and state remain uncertain. Laboratory experiments cannot yet match the hundreds of millions of atmospheres of pressure deep inside this planet. Overall, about 90% of Jupiter by atoms is hydrogen, around 10% is helium, with only a sprinkling of heavier elements. Trace amounts of methane, ammonia, water, and other molecules subtly influence its colors and temperatures, but hydrogen truly dominates. Jupiter spins faster than any other planet in our solar system, completing one rotation in just under 10 hours. Because it is not solid, the equator rotates slightly faster than higher latitudes, a phenomenon called differential rotation that helps organize its banded appearance. That rapid spin stretches Jupiter outward at the equator, creating a noticeable equatorial bulge. It also drives powerful jet streams that whip around the planet in alternating directions, neatly aligning with the bright and dark bands we see from Earth. The same physics that organizes Jupiter's jets also shapes Earth's weather. Coriolis forces from rotation steer our trade winds, jet streams, and hurricanes, just as they channel Jovian clouds, reminding us that one set of physical laws governs both worlds. As a child, it is easy to imagine Jupiter catching fire like a star, since it is mostly hydrogen. But stars are not flames, they are nuclear fusion reactors. Jupiter would need roughly 75 times its current mass to ignite hydrogen fusion. At masses between Jupiter and true stars live brown dwarfs, objects that briefly fuse deuterium but never sustain full hydrogen fusion. Jupiter's radius is not far from the smallest red dwarfs, showing that adding more mass mainly increases density rather than size in this regime. Jupiter also possesses rings, though they are much fainter than Saturn's. There are 4 main components. The brightest is a thin main ring about 6,500 kilometers wide, flanked by hazy, very low-density halo, and gossamer rings spreading outward delicately. Embedded in the main ring is a subtle feature called the Metis notch, a slight dip in brightness where the tiny moon Metis orbits. Impacts on small inner moons likely kick dust into space, replenishing the rings with fresh material over time. Another of Jupiter's extremes is its magnetosphere. Generated by the motion of metallic hydrogen, its magnetic field at the cloud tops is about 14 times stronger than Earth's, inflating a vast bubble in space that dwarfs the Sun's own visible disk. Magnetic field lines guide charged particles toward the poles, where they collide with Jupiter's upper atmosphere and trigger intense auroras, far brighter than Earth's. The 4 large Galilean moons orbit well within this magnetosphere, sheltered from much of the direct solar wind. But inside this protective bubble, trapped charged particles form powerful radiation belts around Jupiter. Spacecraft that venture through these regions endure intense bombardment, which can damage electronics and shorten mission lifetimes, making close exploration of some orbits extremely technically challenging. The innermost large moon, Io, plunges through the heart of this radiation environment. Instruments estimate doses around 3,600 rem per day at its surface, a level that would be quickly lethal for unshielded humans, but which Io's rocks and ices endure continuously. Beyond Io, Jupiter hosts an extended family of moons. At last count, astronomers have confirmed more than 67 natural satellites. Most are tiny, irregular chunks only a few kilometers across, likely captured leftovers from early solar system construction and later collisional debris. The 4 largest, discovered by Galileo, are worlds in their own right. Io is intensely volcanic. Europa likely hides a global ocean beneath ice. Ganymede, larger than Mercury, has its own magnetic field. Callisto is heavily cratered, preserving ancient solar system history. When telescopes study Europa and Ganymede, they are examining water and ice shaped by the same physics that governs Earth's oceans and glaciers. Potential subsurface seas there remind us that habitable environments might exist far from any traditional habitable zone around a star. In infrared light, Jupiter looks different again. Warm regions glow brightly, revealing deep atmospheric structure. Occasionally, observers spot new circular marks, signatures of objects that plunged into the planet, their energy dissipated high in the atmosphere rather than on a solid surface. Impacts like these are reminders of Jupiter's role in intercepting stray bodies. An object large enough to leave a visible scar on Jupiter could significantly alter conditions on a smaller world, yet here its energy is dispersed deep within a giant atmosphere instead. So Jupiter is both a sculptor and a shield, shaping the asteroid belt, steering comets, and modifying planetary orbits. Without a giant like this in our system, the inner rocky planets, including Earth, might have experienced a very different bombardment history. In school, Jupiter is often reduced to a big striped ball with a red spot. In reality, it is a complex system of storms, rings, fields, and moons, a gravitational heavyweight that quietly organizes and sometimes protects the rest of the solar system. Thank you for exploring Jupiter with the universe and beyond. If you want more deep dives into our solar system's hidden mechanics, consider subscribing and supporting us on Patreon, where you can watch ad-free, suggest topics, and help shape future episodes.